Test 3 skill consists solely of a proof procedure called natural deduction. It's in either chapters 9 or 10, depending on what textbook you have, what edition of the textbook you have. First thing you need to acquire in order to do this procedure is to understand this substitution method that we spoke of at the beginning of test 2 instruction. So we said that lowercase letters of the alphabet are simple statement variables, and we'll be substituting actual statements for them to produce arguments. There are two rules that you have to remember for the substitution procedure. Rule number 1 is simply that any actual statement can be substituted for a simple statement variable. So without writing out actual English statements, we'll just use the uppercase letters. So if I substituted the simple statement G for the variable P, we generate the statement G by substitution. If I substitute the compound statement G dot R for P, we generate G dot R. I'm just demonstrating that absolutely any actual statement, simple or compound, can be substituted for a simple statement variable. Our simple statement variables also occur in compound statement forms. So we can substitute for the variables P and Q in the conjunction statement form. We can substitute the simple statement G for the variable P, the simple statement R, and the simple statement R for the variable Q. That would generate, of course, G dot R. Still, a compound statement can be substituted for a variable. So I substitute the conjunction G dot R for the variable P, the conditional statement T horseshoe V for the variable Q in the conjunction statement form. We would generate that conjunction. Is there any question about that substitution? Curl P is a compound statement form called negation. You can substitute anything for the variable P. So obviously, if I substitute G for the variable P in that compound statement form, we would generate curl G. If I substitute curl G for the variable P, that would also generate curl G. Do you understand why? In each case, we're only substituting for the variable. So if we substitute G for the variable P in the statement form curl P, can't do anything about that curl. It's got to remain. You're substituting for the variable. So that would generate curl G. But the compound statement curl G for the variable P would also generate curl G. Questions about that? What if I substituted the compound statement curl G for the variable P in the compound statement form curl P? What do you think I would generate? No. Why do you say G?
Because it's a double negative.
Yeah, you're not allowed to do that. That's why I'm pointing this out. So if I substitute curl G for the variable P in the compound statement form curl P, what do we generate?
Would it be curl of apostrophe. I mean, never mind.
Well, how about curl, curl, G?
Oh, okay. You don't have to put the second curl G in. Never mind.
The second?
It's all good. Don't mind me.
Well, is there any question about that?
So does that translate this?
No. Forget about it.
So it's not,
Pardon?
so it's basically just invalid before it invalidates the argument that it's part of?
No.
How would we translate curl, curl, G?
I'm not sure what you mean by translate. Do you want an example of curl, curl, G?
Yeah, sorry.
Okay.
I just,
Sure.
I guess it could mean anything really.
Sure. It's false that Jean Grey is from Georgia. I'm sorry. It's false that Jean Grey is not from Pennsylvania. So that would be curl, curl, P.
Huh.
Pennsylvania. Curl, curl, G. Sure. Were you questioning, do we have statements like that in English? Oh, absolutely.
Well, no, that makes sense now.
Yeah, we absolutely do. If somebody makes the claim that some statement is false, and I deny that, I'm saying it's false that it's false. Sure. Okay, so rule number 1. Absolutely any actual statement, simple or compound, can be substituted for a simple statement variable. There should be no problem with that. Just remember you're substituting for the variables and none of our connectives or the operator curl. The second rule, where the same statement, the same simple statement variable occurs more than once in a statement form or an argument form, you must substitute the same actual statement for the same variable. Or we can say your substitution has to be consistent. If I substitute the simple statement G for the variable P in this statement form, I have to substitute that same statement G for the variable P everywhere it occurs. And I can substitute anything for Q. Anything. So this is not an allowable substitution. So we're violating our second rule. Do you all get that? Substituting the same actual statement for different variables. Well, let's see what you think about this. No need in making this any more complicated than necessary. Is that a good substitution? What rule have we violated? Well, the second rule says the same actual statement has to be substituted for the same variable, which I did. Right? G for P in both occurrences of P. So, is this a good substitution? If it's not, then I violated one of our two rules. Rule number 1, absolutely anything can be substituted for a simple statement variable. Rule number 2, the same actual statement has to be substituted for the same variable. Have I violated either of those rules? Well, the answer is no. That's a good substitution right there. You need to remember that. That's a good substitution. You can do that. Do you understand that it's not violating either of the only two rules that govern our substitution? Yes? Go to the .cam. I want to look at an exercise that has you identify substitution instances of argument forms. If you have the 12th edition, this is nicely arranged in facing pages on pages 362 and 363. Unfortunately, in the 12th edition, it's not. I think one of these pages might be 344 in the 14th edition. Can somebody look at page 344 in that 14th edition and tell me what you have there? Is that 344? Can I have a look? Okay, it's split between 344 and 345, but that's just one of our pages in the 12th edition. So for this exercise, I'm going to show you the 12th. It's more convenient. But if you want to try it on your own, you're going to have to find some presentation of the rules of inference, elementary valid argument forms in the 14th edition. I can tell you they're on the inside back cover of the book.
It's 243.
It's 243, so you're going to have to flip. 343? Okay, so you're going to have to flip back and forth if you have the 14th edition. Not you folks at home, because we're going to show you both pages in the 12th edition. Let's see if we're on here. Please don't have personal conversations during class. Okay? Thank you. All right, the second thing you have to know is for our proof procedure are these 9 rules of inference. You've got to know them. You've got to know how we use them. Do whatever it takes, to acquire this information. It's not a whole heck of a lot. But these are 9 valid argument forms that you need to know the names of, the abbreviations, and either sight recognition or a verbal description of how they appear. So for example, modus ponens there has 2 premises. The first premise is a conditional statement. The second premise is the antecedent of the first. And the conclusion is the consequent of the first premise. Any argument that's a substitution of that argument form has the same basic description. Can't change that. So once again, modus ponens has 2 premises. First premise is a conditional statement. You understand if you're substituting for the variables p and q, there's no way you can change the fact that it's a conditional statement. Right? The second premise of modus ponens is the antecedent of the first premise, and the conclusion of modus ponens is the consequent of the first premise. So before we continue describing these, I just want to show you an example of a substitution of modus ponens. Number 11 there. It's an actual argument that has been made by this substitution procedure. You'll notice that it has 2 premises. That first premise is a conditional statement. The second premise is the antecedent of the first premise. And the conclusion is the consequent of that first premise. So the same basic description of modus ponens, the argument form, that would have to be the same description of whatever argument is made from it by substitution. You can see that A horseshoe B has been substituted for the variable P in each case, right? And C wedge D has been substituted for the variable Q in each case, right? Okay, let's continue our description of those argument forms, and then we'll try this exercise. Modus tollens has two premises and a conclusion. The first premise is a conditional statement. The second premise is the negation of the consequent of that first premise. And the conclusion is the negation of the antecedent of that first premise. Yep? Are you following my description? Hypothetical syllogism has two premises. Both of those premises in the conclusion are conditional statements. The antecedent of the conclusion is the same component as the antecedent of the first premise. The consequent of the conclusion is the same component as the consequent of the second premise. And those other two remaining components, consequent of the first, antecedent of the second, they would have to be the same component. Whatever argument is made from hypothetical syllogism by substitution would have the same basic description. Disjunctive syllogism has two premises. The first premise is a disjunction. The second premise is the negation of the left-hand disjunct. And the conclusion is the right-hand disjunct of that first premise. Good? Are you able to follow the description? Constructive dilemma. Again, two premises. The first premise is a conjunction of two conditional statements. The second premise is a disjunction of the antecedents of those premises, right? And the conclusion is a disjunction of the consequence of those conditional statements in the first premise. Good? Am I describing it correctly? Absorption has only one premise. It's a conditional statement. The conclusion is also a conditional statement whose antecedent is the same as the first premise, the antecedent of the first premise, whose consequent of the conclusion, the consequent is a conjunction of the antecedent and the consequent of the first premise. Simplification has only one premise. It's a conjunction. The conclusion is the left-hand conjunct of that premise. Conjunction has two premises. They could be anything, right? Because anything could be substituted for the variables P or Q. Conjunction has two premises, and its conclusion is a conjunction of those premises. And then the last one, addition, has one premise. That could be anything. But the conclusion is a disjunction of that premise. And how do you think we should finish off the description? And what? Anything. Right. Addition as one premise could be anything. Its conclusion is a disjunction of that premise and anything whatsoever. So what we want to do with these arguments on the next page is to recognize what argument forms they're substitutions of. Let's see. Argument number 1 has just one premise, so that eliminates most of our 9 rules. How can we describe that? Well, that premise is a conditional statement, and the conclusion is also a conditional statement. The antecedent of the conclusion is the same as the antecedent of the premise, and the consequent of the conclusion is a conjunction of the antecedent and the consequent of that premise. So what are we describing there?
Absorption.
That's absorption. Do you need to be able to describe them? No. Sight recognition is what we're after. To continue in this column, number 3, let's see, we have just one premise. That eliminates a lot of our 9 rules, most of which have 2 premises. The conclusion, however, we notice it's a conjunction, a disjunction of that premise and something else. So what are we describing there? What argument form? That is addition. Number 5. Well, it looks pretty long, but it has the same base description as one of our 9 rules of inference. Let's see what we have here. We've got 2 premises. Notice that first premise is a conjunction of 2 conditional statements. Second premise is a disjunction of their antecedents. And the conclusion is a disjunction of their consequence. Constructive dilemma. All right. Number 7. Again, it looks pretty long, but it's got the same basic description as one of our 9 rules. We've got 2 premises there. That first premise is a disjunction. The second premise is a negation of the left-hand disjunct of the first premise. And the conclusion is the right-hand disjunct of the first premise.
Disjunctive.
That's disjunctive syllogism. See if we're on board here for number 9. And we are. Number 9 has 2 premises. Both of those premises and the conclusion they're all conditional statements. The antecedent of the conclusion is the same as the antecedent of that first premise. And the consequent of the conclusion, where are we at? The consequent of the number 9? The consequent of the conclusion is the same as the consequent of the second premise. And those are the same components. So we're describing hypothetical syllogism. I think we already noted that number 11 is modus ponens. Number 13, you tell me. What are we looking at here? It is modus tollens. It's a pretty long substitution, but same form, same description. about number 15? Again? That's conjunction. It's a long substitution of conjunction. Remember when we described conjunction, we said it has two premises. Either one of those could be absolutely anything. It just says P, Q, therefore P and Q. So that's what we have here. That's substitution for P. That's Q. And here we have their conjunction. There's P and Q. That is conjunction. Oh, what's this guy doing to us? What's number 17? It is absorption. You've got one premise. It's a conditional statement. The conclusion is a conditional statement whose antecedent is the same as that of the premise. Consequent of the conclusion is a conjunction of the antecedent and the consequent of that premise. Tell me what you think about number 10 there. Well, let's see. The description of hypothetical syllogism is that it's got two premises, and both of those in the conclusion are conditional statements. Then we said that the antecedent of the conclusion is the same as the antecedent of the first premise. That doesn't seem to be the case. And we said the consequent of the conclusion is the same as the consequent of the second premise. So it doesn't seem to fit that bit, huh?
Yeah, it's kind of reversed.
Okay, the author is pointing out something to you that actually is important to our proof procedure. These represent actual arguments. That's why we're using uppercase letters. So we're to understand that, in theory, these have been translated from English language arguments. That's why we use the uppercase letters. What the author is pointing out to you is in actual arguments, your premises and conclusion can be stated in any sequence. The conclusion doesn't even have to be last, right? So this has been made from hypothetical syllogism. It's just that the premises of the actual argument have been reversed in order. Got that? Can you recognize it as hypothetical syllogism with the premises reversed? Check it out. Good. This is an example of our proof procedure. It's been translated from English, apparently, presented vertically like we do for this procedure. We number the premises. We always put the conclusion last, after the three-dot symbol for therefore. Doesn't matter where that conclusion occurred in the actual argument. It comes after all the premises. Lines 6 through 8 are the actual proof. So what I want to do now is I'm going to go to the board, turn off the doc cam, and take a moment to copy this down and explain what we mean by this notation. The theory of this proof procedure is exactly the same as what you did in a geometry class if you've had one and done proofs. It's the same procedure. We just have different symbols. And so if you did a proof in geometry, you might have been asked to prove the degree of arc of some angle, which was not given. But maybe some other degrees of arcs of angles were given. And so you use axioms, postulates, and theorems to work your way to the conclusion. You're using valid reasoning in a geometry proof. And we are here as well. So what we're being asked to show here is that the conclusion of the argument E does in fact follow validly from these premises and any other premises that can be derived from them through valid deductions. So that's what the author has done. We're not going to discuss right now how he knows how to do it. I just want to explain what this notation is. So it's absolutely essential that you get this before we start our proof procedure. This notation right here means that the author drew that line 6 as a conclusion from hypothetical syllogism, using the premises in lines 1 and 2 as substitutions for the premises of hypothetical syllogism. So look at your hypothetical syllogism in your book or your notes, and you'll see that that is, in fact, what is happening. You should all recognize that as a substitution of hypothetical syllogism. This notation right here means that the author concluded line 7, again by hypothetical syllogism, this time using lines 6 and 3 as the premises. So do you recognize that as a substitution of hypothetical syllogism? Yes? Okay, I want to point out something that's crucial about the sequencing of this numbering in your notation. The sequencing of the numbers in your notation have to reflect the order in which you use the premises in your argument form. So it says 6-3 because line 6 is used as the first premise of hypothetical syllogism. And line 3 is used as the second premise of hypothetical syllogism. So the sequencing of your numbers has to be correct, or that line of proof is wrong. And you can't use it for further deductions. So is there any question about why that says 6-3 and not 3-6? Do you all understand that 3-6 is wrong? Okay, good. Let's see if you can produce what that notation indicates, like I just did with lines 6 and 7. Got it? It's telling us at line 8, curl A,